So here's the chart from our class. So, which one was dominant? The yeses or the nos? Which one? Jordan? The yeses are dominant. That's just how it was here. So here we see detached earlobes. We see tongue rolling. We see right-handedness. We see, what else is one that we see more of? We see allergies. We see straight hairline. And we see cross left over right. Look at all of those examples of dominant, right? But sometimes the recessive has more. For example, no cleft chin, no freckles. These two were twins. They had the same amount. No dimples on cheeks, right? Now, does the dominant always take over the recessive? Does it always cover it? No. What do we think?
Yes.
Yes. If there is any dominant, if there's any capital letter, if your genotype has any dominant, you're dominant. That's what it is. But does that mean that dominant is always most common? No. Here's 3 examples right here where dominant is not most common. Titus brought up this Punnett square where he had 2. And what are these parents? What would we call them? You know, when we were learning about them, what's their genotype? What's the parents' genotype, Sammy? What's the parents' genotype? Yes. Heterozygous. Exactly. They are heterozygous because they are both different. Heterozygous. Now, Titus pointed out when you mix 2 heterozygous parents, there's a 25% chance you'll get a recessive gene. But that still doesn't fully help us out because that's still a pretty low chance. Here is a Punnett square that I'm going to show you about, and you're all going to get a kick out of this. Are you ready? So, I'm going to tell you this for we're going to talk about fingers, right? Now, who in this class has 5 fingers? Raise your hand if you have, on one hand. Yeah, I meant on one hand. Who has 5 fingers on each hand? Raise your hand. Who has more than 5 fingers on each hand? Who has more than 5 fingers on each hand? So, 5 fingers. Everybody in the class had 5 fingers. So, do you think 5 fingers is dominant or recessive? If everybody had it, what do we think? Let's say it together as a class. Ready?
Dominant.
You are wrong. It's recessive. How does that make any sense? Everybody in this class has 5 fingers, and dominant covers up recessive. How does that make any sense? Marco?
Because both of your parents probably have 5.
Exactly. If your parents have 5 fingers, the only way you can be recessive is to have both of the recessive types. When something is recessive, does it look like this? Does it look like this? Or does it look like this? Which one? 1, 2, or 3? Clover? 3, right? Looks like this one. So, if your parents have 5 fingers, and this is the recessive gene, remember it's recessive. If your parents have 5 fingers, what would their genotype be? First, what's mom's genotype if they're the recessive type? I know it's a little confusing. What is it going to be, Marco? He said great. He said homozygous recessive, which is great. Now, if your parents have 5 fingers, the only outcome here, that's 5 fingers. These 2 are 6 fingers. So, if your parents have 5 fingers, what is going to be their genotype? If your parents have 5 fingers, what's going to be their genotype?
Recessive.
Yes, it's recessive, but genotype, what are the letters? Yes, Matthew. Not the hetero. What is it going to be? Yes, Sophia. Yes, we said that. Here's what it's going to look like. Everyone's parents have 5 fingers, right? The only way you can have 5 fingers is by having the 2 small d's. So here I'm going to do it in color to make it even better for us because I love it. We have 2 small d's. That's your dad. Your dad has 5 fingers, so he has both recessive genes. What about your mom? She has 5 fingers, so she has both recessive genes too, right? So look what happens. Look what happens.
It's always going to be the same.
It's all recessive. So is there even a chance of having 6 fingers? Is there a chance of having the dominant? No. So in many situations, such as cleft chins, such as the other stuff that we brought up, freckles and dimples, a lot of times it's less common for that. So for example, if I was looking at this Punnett square, you might have a parent that looks like this. If you had a parent with a cleft chin, there's a chance they have to have that dominant gene, but they'd have the recessive gene. But your other parent would have both the recessive, because that's the only outcome if you don't have a cleft chin, right? Which means we bring this down, we do our Punnett square as we do it, and what percent chance is there of having a cleft chin? What percent, Zoe?
50.
50%, which then leaves us still with 50% of not having a cleft chin, So in these situations, it's stuff like this, where if we have a lot of these recessive things here, the more recessive we have, the higher the chance that the outcome of the offspring is going to be recessive. So Taya brought up that when her parents were little, they had curly hair, and now her dad's bald and her mom's got straight hair. So she's wondering, is her hair gonna get straighter? The answer is possibly. For example, this is what baby Miss Diaz looked like. Do you see how curly my hair was?
Yes.
That was my natural hair. Here's another really good picture of baby Miss Diaz. Look at how curly my hair is. That's my little brother, by the way. His name is Ian. And here's the sign inside out. And then lastly, here's me when I was about 7. Look at my hair now.
Whoa.
It's straight. So sometimes your hair changes over time. When Titus asked a great question, that are you going to develop some of the traits like being quick to anger like a parent or something like that? There's two different things. There's nature versus nurture. We also have now started calling it nature and nurture because they both play a huge part. Nature. What is nature? What do you think nature means, Matthew? That it does mean the outside living world. What do you think it means in science, Juliet?
Oh, I think in science, nature means like it's something like, for example, genetics. It happens to you, like, and you can't choose it. But when it's like nurture, it means you learn from it. So,
Yes.
for example, you can't learn to be. I mean, you can learn to be mad, but you can't like learn to have anger.
Exactly. So nature is what you're born with. When you pop out, all of these things of nature are already determined. For example, hair color, eye color, we've got all of that. Even your intelligence, it relates to that. But then there's nurture, and nurture is things that you learn. So you can learn things. They work in conjunction with one another. We used to think that one took over more than the other. Now, to be fair, it's about 80% nature and about 20% nurture. They've done twin studies to prove this, and I'll show it to my twins who are enjoying it. So blood types. I have a chart up there, but we haven't done Punnett squares with blood types yet, and I want to show you this. My father has type A blood. My mother has type B blood. With blood types, just like how we have heterozygous and homozygous, it can happen with blood types too. They could either be heterozygous for A homozygous for A or heterozygous for A. That little I symbolizes O blood. So, my parents, I did a blood family tree once because I'm really weird. And my parents both carry O. And I know this because they both have siblings with O blood. And the only way they could have a sibling with O blood is if the parents carried O, which means the kid had to carry O. It's a whole thing. Now, let's look at it. My dad had A blood. My mom had B blood. So, one of the first outcomes is AB, BI, AI, and II. I means O. That's just how they symbolize it. Now, that means if I cross my parents, there are 4 possible blood types, all the different blood types that they could have possibly gotten. So there's a 25% chance of each blood type, right?
Yeah.
That's the thing. This is recessive, so it didn't show. This is recessive, so it didn't show. But there it is. Somebody could have the recessive blood type. Somebody could have that recessive blood type, even if their parents don't. Same with hair color. Even if your parents don't have your red hair, they probably carry the trait from your grandparents. That's how it gets passed down. Here's me and my husband's blood types. I'll go over it, right? So my blood type is AB. When we fill out the Punnett square, before we do anything, I'm just going to drop the letters. A, B, B. All I did was drop those letters. In this case, I'm going to move them across. My husband has type O blood, so he has both of these I's. We bring those across. What are the outcomes of blood for our children? What are the outcomes, Sitlali? It's a 50-50, but what blood type could our children ever have? What are the blood types our children would have? Who can tell me? Titus, do you know?
Maybe A or B.
A or B. That's weird because my blood type is an A or B. His blood type is an A or B. In fact, if you look, there's a 0% chance that our children will have the same blood type as me or my husband. 0% chance. That's the same thing with red hair. There might be a 0% chance that your parents will have red hair, but they will cover it. As you can see, everybody carries that recessive gene. So for their children, it'll be possible for that recessive gene to pop back out, just like with red hair, just like with this one. So Jada, I want you to fill out this Punnett square.
I think I got it wrong.
Excellent. Who agrees?
Me?
Yes, everybody agrees. You're right. What's the percent of recessive traits? What is the percent of having recessive traits, Taya? 50%. So, based on that, because we're super smart math people, Kai, what's the chance of having dominant traits? 50%. We're going to make these into ratios, too. How many are homozygous dominant? How many on here are homozygous dominant, Marco? Do we agree that?
Yes.
Do we agree? I hear some yeses, I hear some nos. Who disagrees? What do you disagree with, Titus?
That there are two homozygous dominants because
So
they are both in half.
So
You are be one of each.
So is there homozygous dominance? Remember, genotypes. We're talking about genotypes, not the phenotype. Is there any homozygous dominance here? No. Taya said no, and that's correct. Because there isn't any that look like this. Homozygous means same, and dominant is both capital letters. What about homozygous recessive? How many are there, Jordan? Two. And what about heterozygous? What is heterozygous at Lolly? 2. So our ratio would be 0 to 2 to 2. And by the way, with our ratios, how many boxes do we have here? How many boxes do we have? So how many boxes do we have?
4.
We have how many? 4 boxes. So our ratio, if we add them all up, should equal 4. If you're adding them up and you get 5 or 3, do you think you're doing it right? No, you're not doing it right. Sit Lolly. Give me an example of homozygous dominant genotypes. Homozygous dominant genotypes. Never mind, Sit Lolly. Zoe, show me an example of homozygous dominant with those letters.
Wait, so
With T's, the T's. Give me the genotype homozygous dominant.
is it 0?
So Zoe gave us the example of homozygous dominant with 2 capital T's. Excellent! Gia, give me the genotype for homozygous recessive. Homozygous recessive. Try your best.
So
Okay, Matthew, come up and write for homozygous recessive. What would our genotype be?
I'm thinking it is.
Who agrees? Yes, perfect. Lastly, Taya, come up here for heterozygous. Taya, come up here for heterozygous. So for heterozygous, we get... Excellent. So these are the traits that we have. They're in your notes as well. So what are these known as? What are these letters? What do we call them? They're besides homozygous, besides that. What do we call them? What do they represent, Sammy? They do represent genetics. And what is that word? What is that word that we hear? Marco? Genotype. Yes, genotype. And we can remember because it's got genetics in it. So now let's think about this. We're going to go and look at this again here. but I'm going to change it a little so we can have room. Now I want to talk about the other thing, the appearance. Is this one going to be dominant? We already know this. Is this one going to be dominant? Yes. Is this one going to be dominant?
No.
No, it's recessive. Is this one going to be dominant?
No.
Yes. So Marco, how did you know that it was dominant?
Because it has the capital T.
It has the capital T. It has the capital T, which means it's dominant. If it has any capital letter, it's dominant. If it doesn't have any capital letter, it's recessive. So then, what if I was talking about what it looked like? What if I was talking about what it looked like? Let's say the big T stands for tall and the little t stands for short, right? What is that called when I'm looking at that? When I'm looking at this one and I get this person to be tall, this person to be short, and this person to be tall. What am I asking about? What am I talking about? What is that term called? Marco? Phenotype. And how do we remember phenotype? How do we remember the word phenotype? Yes. Physical appearance, so that PH for physical. Thank you, Sit Lolly. So if we filled out these Punnett squares, remember we drop and we go down, we would get capital D, capital D, capital D, capital D, capital D, little d, capital D, little d. The phenotypes. How many are dominant? How many are going to be the dominant trait here? Jordan. 2 are going to be the dominant? Who agrees? Who disagrees? So what is it going to be? How many are going to be dominant? 4. All 4. 100% are dominant because each of them has a big D. This next one here, if we filled it out, these have both capital F's. So I need a capital F here, and a capital F here, and a capital F there. But here I've got a lowercase f. So I have to put a lowercase f, and this becomes that as well. Same kind of chart, 100% dominant. 100% dominant. So you guys need to be able to identify percentage of what's dominant and recessive, genotypes, phenotypes, etc. Perfect. Study for your test. Use your notes. The way that we do reverse Punnett squares is when we have only partial information. Normally, with Punnett squares, we have the information of both parents and need to find the information about the offspring. For reverse Punnett squares, we have typically 4 pieces of information out of our 8 pieces, and we have to reverse engineer the problem. So let's take a look at this one first. We have our little a here, and we have a little a here. But we still have that extra one, which means that we need to put that A up top. That's the only way that we can get the 2 recessive traits right down there. As such, we'll have an A here and an A here following through like that. Now, we also have this A here. Here, we have a capital A, which means that we're going to have that here on the side, which gets filled out there as well. So that's how we would do one example of a reverse Punnett square. As for the second example of our Punnett square, we're still searching for 4 pieces of information. What we do have is we have our capital F for one of our parents, which gets dropped down here and here. As we know, this one has another capital F, meaning this one has to be capital, as well as one of ours over here. Here we have our little f and our capital F. Capital F is already taken with this one, so our little f has to be here. That also makes sense because we have 2 little f's down there. The only way we can get 2 little f's is by having both of those be the little f, which follows through that this then becomes as such. We would then have 1 homozygous dominant, 1 homozygous recessive, and we would have 2 heterozygous hybrids. In this case, 3 of the 4 would show dominant traits, and only 1 would show the recessive. If we were to write this as a ratio for dominant and recessive, it would be 3 to 1. If we were to write this as a ratio of genotypes, it would be 1 to 2 to 1. 1 for our homozygous dominant, 2 for our heterozygous hybrids, and 1 for our homozygous recessive.